Welcome to Lecture 14, The Method of Sections. In this lecture, I'll be discussing the use of the method of sections in the analysis of simple trusses. In the last lecture, I discussed using the method of joints to analyze simple trusses, and the method of joints works fine, especially when you need to find the forces in all the members in a truss, or if you have a small truss, a truss without a large number of joints, and you only need to find the forces in a few specific members of the truss, the method of joints is still, probably the way to go. But suppose we are asked to find the force in only a few members of a large truss, a truss with a large number of joints. Think of specifically a large truss where we're asked to find the force in just a few members in the middle of the truss. So in this case, the method of joints will work, but we're going to spend a lot of time working joint by joint from the support reactions, the joints where the support reactions are present, to the area of interest. So we have another method known as the method of sections that is useful when we are trying to find the force in only a few members of a truss, more specifically a large truss. The method of sections involves dividing a truss into two parts by taking an imaginary cut through the truss. In the figure here, we've shown this imaginary cut as AA, and notice that the cut separates the truss into two distinct parts. We can't just cut BC and GC. We have to cut all the way through the truss. We've already established that truss members are either in tension or compression, unless they happen to be a zero force member, and that those tensile and compressive forces act along their length. So if we cut through a truss member, the force that we would show at the cut in a free body diagram is no different from the force we would show if we removed that member from a pin joint. It'll be the same magnitude and same direction. So let's look at a truss member in tension here. If we take a cut through that member and drew a free body diagram of the top half of the member after the cut, we still have the same force T acting there, and that would have to be balanced by a force, an equal force T in the opposite direction. And if we had removed this member from a pin up here at this, where this joint would be, where this would be in a joint, we would show that same force T in that same direction on that pin in that joint free body diagram. Same thing for compression. We cut through a truss member in compression, then the free body diagram of the top half has to show a force equal and opposite to the pre-existing force C in order to maintain equilibrium. Now, this is all based on the equilibrium principle and Newton's third law, and really shouldn't be anything new given where we are at this point in the course. Let's look at the steps for simple truss analysis when using the method of sections. The first thing you need to do is determine how you need to cut the truss. And you're going to base this on where you need to determine forces and where such a cut will leave no more than 3 unknowns. Okay, So let's suppose for this figure here, we were asked to find the force in member GC. We know we're going to have to cut through GC, but our cut needs to leave us with two distinct parts of the truss. In other words, we can't leave anything from the first part connected to anything on the second part of the truss. So if we make a cut through BC, GC, and GF, I've satisfied all those conditions. I've cut through GC, which is what I'm interested in. I've only cut through 3 total members, so I'm only going to have 3 unknowns. And the cut has resulted in having 2 distinct parts of the truss. I have everything to the left of the cut and everything to the right of the cut, and those are not physically connected in any way. Now notice that the force in member GC shows up on both sides of the cut, and I can work with either side of the cut to solve for the force in GC. So now I have a decision to make. Do I want to work with the left side of the cut or the right side of the cut? So we want to pick the side that's easier to work with, and hopefully you can see that the left side would be the choice here, because in addition to the 3 unknowns, the only other force I'm dealing with is a known force here at the end of the truss, that 1,000 Newton force, which I know its magnitude and direction. Whereas on the right side of the cut, I've got the support reactions, which are unknown at this point. So to work with the right side of the cut, I'm going to have to do more work to solve for those support reactions first, and then solve for the unknown forces created by the cut. Whereas on the left side, it's going to be more straightforward. So the second step is deciding which side of the cut you are going to work with. The next step is to, if required, determine the support reactions. So you may not have a choice but to work with the side of the cut that involves the support reactions or a support reaction for one reason or another. So you will have to solve for those if the side of the cut you're working with includes the support reactions for the entire truss. The next step in the analysis is to draw a free body diagram of the part of the cut truss that you have selected. So remember, a couple of slides ago, we looked at the part of the truss to the left of the cut and the part of the truss to the right of the cut, which both contain the 3 unknowns, so you can work with either side. And we determined that the left side would be much easier to work with. The right side, in addition to having the 3 unknowns, also had 3 unknown support reactions, so that's just more room for mistakes. And in this example, the left side is just definitely the choice as the side to work with further. Also, as discussed when using the method of joints, it's good practice to, and I highly recommend that you assume that all unknown forces are in tension. Now the author hasn't shown that here. I'm going to override that and show FGF in tension. That way, when you solve for the unknowns, If your answer is positive, you know it's in tension. If the answer is negative, you know it's in compression. So when you see a negative sign and you've assumed everything's in tension and you stay consistent with that, anytime you see a negative sign, you'll know compression. If it's positive, it's tension. If you don't assume everything's in tension to begin with, and you see a negative sign, you're going to have to go back and look at what you assumed and then take the opposite of that. So I highly recommend that you adopt the practice of assuming that all of your unknowns act in tension. The last step in the analysis is to apply the equations of equilibrium to your free body diagram and solve for the unknown forces. Now note here that in the method of sections, we're dealing with a 2D rigid body that's in equilibrium. So we have three equations of equilibrium: the sum of the forces in the x direction, the sum of the forces in the y direction, and the sum of the moments about any point. We can set all three of those equations equal to 0 since we're in equilibrium. Whereas in the method of joints, we were dealing with 2D particle equilibrium, and we just had the two equations of equilibrium to deal with. Also note that when you start solving for your unknowns, there's usually one equation you can write where you can solve for one unknown directly. In other words, you can write an equation that only has one unknown in it in a lot of these method of sections problems, and that should be the equation that you try to write first.